We're going to look at a few examples of how to balance chemical equations. So there's a few rules that we want to follow. The first of which is we want to write a correct skeletal equation. And this just means that we want to write the correct chemical formulas for everything that's in our equation. So we have to start there before we even worry about balancing anything. So let's jump right into the first example. Solid chromium 3 oxide reacts with solid carbon to produce solid chromium and carbon dioxide gas. So the first step is I need to write chemical formulas for each thing in my chemical reaction. So chromium 3 oxide, this tells me that chromium has a 3 plus charge. And I know based on the periodic table, because oxygen is in group 6A, that it tends to form a 2 minus charge. So if I want to put those together to make a electrically balanced formula, then I need to have 2 chromiums, which would make a 6 plus charge altogether, and 3 oxygens, which would give me a 6 minus charge altogether. So I need to make sure before I worry about balancing anything that my subscripts of all of my chemical formulas are correct. So it tells me that this is a solid, and this reacts with solid carbon. So this is just elemental carbon. I need to make sure I include my states of matter, so that is S for solid, to produce. So that means I'm onto my products now. Solid chromium. So chromium, again, is an element, just Cr, and they tell me it's a solid, and carbon dioxide gas. So this is CO2, and they tell me it's a gas. So this is my skeletal equation. I have a correct chemical formula for each compound or each element in my chemical formula, in my equation. And now I'm going to go through and try and balance. So I want to look and see if there's any complicated polyatomic ions. This one doesn't have any. We're going to look at that in a further example. This is also not a combustion equation. So I give a step 3 over here for combustion equations, balance carbon first, then hydrogen, then oxygen, but this is not a combustion equation. And the last thing is balance pure elements last. So that means things like chromium and carbon in this equation. I want to balance those last because if I put a coefficient in front of them, I'm not going to change anything else except that one element. So those things I'm going to balance last. So now if I want to start with oxygen, if I look at the left-hand side of the equation, I have 3 oxygen. And if I look at the right-hand side of the equation, I have 2. So how do I balance 3 and 2? I can multiply them together and put 6 on each side. So if I put a coefficient of 2 in front here, 2 times 3 gives me 6 oxygen. And if I put a coefficient of 3 right here, then I have 3 times 2 gives me 6 oxygen. So at this point, I know my oxygen are balanced, and now I can go and balance my chromium and my carbon. So if I look at chromium next, now I put a 2 here, so now I've got 2 times 2 is 4 chromium on the left-hand side, on the reactant side. And on the right-hand side, I just have 1 so far. So if I put a coefficient of 4 in front, that would balance my chromium. Then I would have 4 chromium on the product side and 4 chromium on the reactant side. Now I can balance my carbon. If I look at the right hand at the product side, I have carbon right here, and I have a coefficient of 3 in front. That subscript of 2 is only for the oxygen. So I have a coefficient of 3 in front of my carbon. That means I've got 3 carbon on the right-hand side. So I need to put a coefficient of 3 on the left-hand side so that I have 3 carbon on that side. So now this is a balanced chemical equation. I have the same number of each kind of element on both sides of my equation. All right, let's look at another example. So step 3 says for combustion equations, balance in this order: carbon, hydrogen, oxygen. That is not a hard and fast rule. It is just usually the easiest way to do the balancing. Ultimately, if you come up with a different method, there's no one right way to balance an equation. There's only a right final answer. So there's only one form of the equation that is correct and correctly balanced. But if you go about it in a different method, if you balance a different element first, that's totally okay. But generally for combustion, the easiest thing is to balance carbon first, then hydrogen, then oxygen. And you'll see that right here. All right, so first we have to write our skeletal equation. It says the combustion of propane, which is C3H8, and it's a gas. So C3H8, and it's a gas. And combustion means burning in air in oxygen. So it burns with oxygen, which is a gas, to form carbon dioxide gas, and water vapor, water gas. So gas, things can be solid, liquid, or gas. Right here, our H2O is going to be a gas because we've got burning going on. And so it's so hot that the water is in the gaseous form, not in the liquid form. All right, so it said start with carbon and then move on to hydrogen and then oxygen. So if I look at the left-hand side of the equation, I have 3 carbon on this side. And if I look at the right-hand side, I have 1 carbon over here. So the first thing I'm going to do is put a coefficient of 3 in front of CO2. So now I have 3 carbon on the left and 3 carbon on the right. Now I'm going to move on to hydrogen. I look over here and I see I have 8 hydrogen. And if I look on the right-hand side, the product side, I see I have 2 hydrogen over here. So if I put a coefficient of 4 in front of that, then 4 times 2 gives me 8. Now, by putting that 4 in front, I also changed the number of oxygen. And the same thing with the carbon dioxide. By putting the 3 in front, I didn't just change the carbon, I also changed the oxygen. So now if I look at both the CO2 and the H2O, I have to add them together. I've got 3 times 2 is 6 oxygen coming from the CO2, but I also have 4 times 1, 4 oxygen coming from the H2O. So I need to add those together. So if I add those together, all together, I have 10 oxygen. And so then I need to go to the reactant side. I have a subscript of 2 over here. So if I put a coefficient of 5, 5 times 2 gives me 10 oxygen on the left-hand side. So now I've got everything completely balanced, the same number of carbons, hydrogens, and oxygens on each side of the equation. All right, let's look at one more example. One of the tips I said was for polyatomic ions, balance them as a unit, and I'll show you what that means. And it's also helpful to balance those polyatomic ions first, rather than doing any of the other elements in your equation. So in this example, aqueous lead 2 acetate. So first we need to write our correct skeletal equation. So we have to figure out what are the chemical formulas of these compounds. So lead 2 tells me that this is lead with a 2+ charge. Now I might not remember what acetate is, but I can go to my table of polyatomic ions and look up acetate. This is C2H3O2, and the whole thing has a 1- charge. So lead acetate, if I put that together and make a compound, I would need 2 acetates for every 1 lead so that my charges would balance. So I would have a chemical formula of PbC2H3O2, but I would need 2 of that entire thing. So it says this reacts, and it says this is aqueous. So I need to include my state of matter, AQ, which means it's dissolved in water. And this reacts with aqueous potassium iodide. So potassium has a +1 charge. It's in group 1A of the periodic table. Iodide is in group 7A, which means it has a -1 charge. So my balanced chemical formula would just be Ki. And it tells me this is also dissolved in water. This is aqueous. To form solid lead 2 iodide, so this is a precipitation reaction. So we know lead 2 is lead with a 2+ charge. Iodide is 1-. So I would need 2 iodine for every 1 lead. That would give me a 2+ and a 2- canceling out. And that's my solid. And then aqueous potassium acetate. So we said potassium was a +1 charge and acetate was a -1 charge. So again, I need just one of each of those together to balance each other out. I'm not worried about balancing the number of each element on each side of the equation right now. I'm not worried about balancing the equation. I am only worried about writing a chemical formula that is correct based on charge. So potassium acetate would be K, and acetate is C2H3O2, and I was told this is aqueous, dissolved. Okay, so now I have the correct chemical formula for all of my products and reactants, and now I need to go through and put in coefficients in front of everything in order to balance. And generally the easiest way to do this is to start with my polyatomic ions. So acetate is a polyatomic ion, and I want to balance that whole thing, if I can, as a unit. So rather than breaking it apart into carbon and hydrogen and oxygen, which gets a little bit complicated, I have this whole thing as a unit on both sides. So I could say that I've got 2 acetates on my left side, on the reactant side, and only 1 acetate on the right-hand side. So in order to balance that, I could put a 2 right here, and now I've got 2 acetates on the right and 2 acetates on the left. So I balance the entire thing as a unit. So from then on, I can go and balance the rest of the elements in my equation. So I usually find it easiest, since I put a coefficient of 2 here, that changed the number of potassiums, right? There was 1 potassium before, now there's 2 on that side. So I'm going to go ahead and balance the potassium. So now since there's 2 potassium on this side, I'm going to go ahead and put a 2 right here so that I have 2 potassium on the left side. Of course, putting a 2 there changed the number of iodine, right? So now I've got 2 iodine on the left-hand side. And look at that, there's a subscript of 2. So I already have 2 iodine on the right-hand side. So that's actually already balanced. And then the last thing that I haven't looked at yet is the lead. If I look at the left-hand side, I have 1 lead. And if I look at the right-hand side, I have 1 lead. So I don't need to do anything to balance that. So this is my overall balanced chemical equation.